So in topic 5, we're going to introduce the graphs of the cosine and sine functions, and we want to start by looking at the graph of f of theta equals cosine theta. We want to understand why the graph of the function looks the way that it does, and we're going to get at this by thinking about on the unit circle. So here I have a unit circle. It's going from -1 to 1, -1 to 1. We want to think about on the unit circle how an ordered pair xy has been defined. So what we want to recall is that any ordered pair xy on the unit circle can actually be described as the ordered pair cosine of theta, sine theta, and this was by a previous result that we looked at in a previous video. So we discovered that x is just equal to the cosine of theta, where theta, this angle theta, has to be the angle in standard position that sweeps out starting at the positive x-axis and ending at the terminal side formed by the point xy. So this is the angle theta. So in function world then, if x is the output to the cosine of theta, if I describe the cosine of theta using function notation, f of theta equals cosine theta, I want to recognize that x is the output to the function. So the cosine function is really generating ordered pairs, input theta, output the x coordinate that is generated when we sweep through an angle of theta around the unit circle. So when I draw the cosine function, which I have drawn in here using GeoGebra, the outputs for the cosine function are really the x coordinates on the unit circle, and the inputs are theta, the angle through which we have rotated as we rotate around the unit circle. Give myself a little more space, and that's going to force me to clean this up a little bit, unfortunately. Always got to make a mistake, right? That's just how life is. Anyways, we want to recognize when we graph the cosine function, which has been graphed for us already, the outputs are the x coordinate on the unit circle, and the inputs are the angle we've swept to get through it. So if I start with 0 degrees right here in standard position, my x coordinate is 1. So I get a signed width here, x equaled 1, which then on the cosine function becomes the output. So this ordered pair on the cosine function is the input 0 degrees, and the output has to be the x coordinate, which is 1. So the length of the red line here, which is the distance from the origin to the x-coordinate, is going to be the same as the length of the red line here, which because the output is the x-coordinate, right? So I'm outputting x on the y-axis, so this distance is always the same as this distance. So when I sweep through, I start to sweep out an angle. So here I'm starting at 0 degrees. If I start to sweep out an angle, going counterclockwise around the unit circle, so I've swept around the unit circle to this point on the unit circle, what I want to notice is that the x-coordinate right now, the x-coordinate is 0.53, and my angle here is 58 degrees. So on the cosine function, this point has to be, what is the angle at that point? Well, the angle at that point is 58 degrees, and the output is the x-coordinate, which is 0.53. So the output is 0.53. The input is the angle, and the output is the x-coordinate. So here, GeoGebra is giving me that input angle in radians, but I can also see the input angle in degrees down here. So as we continue to sweep around the unit circle, we're going to wind up at one point at 90 degrees. So we started in standard position at the 0 degree mark. Now we've swept all the way through around the unit circle through an angle of 90 degrees. So I should wind up with a point on the graph. It should be input the angle, which is 90 degrees, and output the x-coordinate. But what's the x-coordinate up here at the top of the unit circle? Well, at the top of the unit circle, the x-coordinate is 0, 1, right? The x-coordinate is 0. So at 90 degrees, the output is 0, the x-coordinate on the unit circle. And we just continue to sweep around the unit circle. If I continue to sweep around, at some point I hit the 180 degree mark. So at a 180 degree rotation, this point on the unit circle is -1, 0. So at the 180 degree mark, the output on the cosine function should be, hey, after you've swept through 180 degrees, the output's going to be an x-coordinate of -1, or after you've swept through pi radians, the output's going to be an x-coordinate of -1. And then we're going to sweep out to the 270 degree mark, and at 270 degrees on the unit circle, we have the ordered pair x is 0, y is -1. So we should, at the 270 degree mark, get an output of 0 because the x-coordinate on the unit circle is 0. And then we sweep all the way through to 360 degrees, we're back where we started. We're at an angle that's coterminal with 0 degrees. So when we sweep through to the 360 degree mark, we should be getting a point input 360, output 1 again, or input 2 pi radians, output 1 again. And what we notice is that between 0 and 360, because we've swept all the way around the unit circle, the graph of cosine, which describes the x-coordinate, is all the way back where it started. So we say that the period of the cosine function is 2 pi radians, or 360 degrees, because everything that can happen to the x-coordinate on the unit circle has happened to it through a 360 degree rotation, and then everything just happens all over again. So the cosine function is just going to continue on and on and on and on forever to the right, repeating the same pattern over and over again, and it's going to go on and on forever to the left, repeating the same pattern over and over again. Got to get everything to line up. No, it's not going to line up now. I messed that up by moving it. Let's go off into PowerPoint and kind of summarize what we just did. So I'm going to wipe that screen clean, close the pen, and open this up. So here's the idea. If you're going to graph the cosine function, so we'll take it out of GeoGebra. The graph of the cosine function comes from rotating around the unit circle. There's the unit circle. And we want to think about the quadrantal angles as key features on the unit circle. So input 1, output 0, input 0, output 1, input -1, output 0, and here input 0, output -1. So as we rotate at 0 degrees, we're always starting at 1. When we get to 90 degrees, we'll be at 0, right? So we always start at the x-coordinate being 1, and then the x-coordinate, holy schmack. We always start with the x-coordinate being -1, so we want to remember we're plotting the x-coordinate on the vertical axis and the angle on the horizontal or input axis. And at the 90 degree mark, we have an x-coordinate of 0, so we'll be on the theta axis where x is equal to 0. And we continue to rotate, x is going to hit a low point at -1, and then we rotate back through. X is going to be at 0 again, so I have to come back to the theta axis where x is 0. And then when we get to 360 degrees, we're back where we started. And this will always be the case. We start at a height of 1, we end at a height of -1, and we move from 1 to -1 and back to 1 over 360 degrees. And the key features we see here, the peaks, the valleys, and the zeros, all correspond to the quadrantal angles. So they're really easy to get. This is the 90-degree mark. This low point happens at the 180-degree mark. We're back at 0. The x-coordinate is back at 0 at the 270-degree mark. And we're back where we started at the 360-degree mark. So these are all multiples of 90. 90 times 1, 90 times 2, 90 times 3, 90 times 4. And if we were in radian world, 90 degrees is the same as pi over 2 radians. And then we can just count up. These will just be multiples of pi over 2. This will be 2 pi over 2, 3 pi over 2, 4 pi over 2. And notice 4 pi over 2 would reduce to 2 pi radians, which is equivalent to 360 degrees. And 2 pi over 2 reduces to pi radians, which is equivalent to 180 degrees. So we want to recognize that the graph goes on and on forever. Once you rotate around the unit circle again, you just rotate around another time and another time, and you can rotate positive theta, or you can rotate clockwise, which gives you negative values of theta. So the graph repeats itself infinitely far in both directions. In general, when you're going to graph the cosine function, here's my tip. If you're hand graphing it and not using a calculator. So I think the thing that students do that makes their life miserable when they're graphing, and not just for trig functions, but graphing in general, I think putting tick marks on the x and the y axes, or the x and the theta axes, or whatever your input-output axes are, up front is a mistake. What you want to do is think about, what does the function look like? Okay, what does the cosine function look like? And then you just draw it, right? And we want to recognize that this is going to be, for cosine functions, this is going to be our toolbox function. This is going to be the toolbox function. Simplest possible cosine function that you can draw. And so the cosine function, the toolbox function, always looks the same. You start high because x is 1 at 0 degrees, and you rotate through to a low point, and then you rotate back through to a high point. This is going to happen every time, and you just do this you do this a few times till you get kind of good at drawing it. I'm a terrible artist, so I can never get it super nice. But the idea is, it starts high, goes to its low point, it has to come back to where it started. And then once you've drawn what the graph has to look like, then put your tick marks in. Hey, it goes from 1 to -1 because it's the cosine function, and it does it in 360 degrees, or 1 revolution around the unit circle. And these key points, the high points, the low points, and the zeros, all are multiples of 90 degrees, or pi over 2 radians. So this is just 90 degrees, this is just 180 degrees, this is just 270 degrees. And we get this base measure, the first tick mark, we get by dividing the full revolution by 4, because we're broken into 4 chunks. 1, 2, 3, 4. That gives us our 90 degrees. If we're in radians, pi over 2, or 90 degrees, is the first chunk. And then you just count up. Here's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And sometimes it actually makes sense not to reduce these, depending on the application, but you can always reduce them into simplest form after you've counted up. So that's the easiest way to draw the cosine function. First draw the shape, then put the tick marks in, so that you're not trying to bend the graph to fit tick marks that you've already put there. So domain of the cosine function, remember, domain is possible inputs, so the inputs are theta. So when we're asking for domain, we're saying, what can theta be? Well, it turns out that theta is just you're rotating around the unit circle. Well, how many times and remember, counterclockwise rotations are positive. Well, how many times can you rotate counterclockwise? Probably infinitely many times. And then negative values for theta are just clockwise rotations. Well, if I start in standard position and I start rotating clockwise, how many times can I do that? Well, there's no limitation on it. I can rotate as many times as I want. So the domain is going to be, theta can be anything from negative infinity to infinity because there's no restrictions on how many times we can rotate. But the range is what can x be, right? The outputs are the x values. Well, x is going to range from a low point of -1. That's as far as the x-coordinates can get on the unit circle. And the furthest an x-coordinate can get on the unit circle is +1. So the range is going to be from -1 to 1. And in trigonometry, the period just is answering the question, over what angle does everything happen in the picture that's going to happen? And so the period is going to be 360 degrees, or 2 pi radians, 1 revolution around the unit circle.